So again, our course is multivariable and vector calculus. And since it says calculus on the tin, when we open it up, we expect to see things that we remember from single variable calculus. And so in our last class meeting, we talked about limits in the multivariable context. And having satisfied some of our curiosity about limits, we're not going to do a whole lot as it comes to limit computations in our course. If you take a course in real analysis later on, if you're a math major, some real analysis courses end up getting all the way to sort of multivariable calculus and popping the hood and sort of seeing what is it underneath all of that limit stuff that we talked about on Thursday that really powers calculus in a multivariable setting. But we're not going to do much more with that because our goals for this course are a little bit more computational than that. And so having had one day on limits, we're going to charge ahead this class and get to derivatives. And so today is all about our first notion of what should a derivative mean in a multivariable context for a function of several variables. And interestingly, so our textbook is called Multivariable and Vector Calculus, and there are some cases in which I tend to see those two things as one and the same thing. But I think the story of the next couple of class periods is going to be that today we're going to treat the question of derivative as really more of a multivariable kind of question. We're not going to see vectors come in and sort of help us with the sort of geometry of what we're doing today. But when vectors arrive at the party tomorrow and the day after, they're going to give us a really powerful way of understanding derivatives of functions of several variables in their full sort of geometric flourish. So for today, we're going to talk about an idea, a concept of derivative that resembles very closely our idea of what derivative meant in a single variable context. So today is all about partial derivatives, which is going to be derivatives that we can take of a function of several variables where the input variables are changing one at a time. So if my function depends on both x and y, when I take a partial derivative, that partial derivative is going to be a derivative where only x is allowed to change and y cannot change. Or vice versa, where only y is going to be allowed to change and x doesn't change. So when we only let one of the variables in a several variable function change at a time, then the resulting rate of change of the output per unit change in the input gets called a partial derivative with respect to that coordinate direction. So a function of x and y is going to have a partial derivative in the x direction, and it's going to have a partial derivative in the y direction. A function of x, y, and z will have one each in the x, y, and z directions, right? And so that's the idea of partial derivative. And the really good news is that computationally speaking, we're not going to have to do really hardly anything new compared to single variable calculus to understand how to compute a partial derivative. The only thing we need to do is sort of suspend our disbelief temporarily that one or more of my variables is actually a variable. We treat it like a constant and only let the one variable that we're interested in changing act as a variable. So when vectors arrive at the party tomorrow and the next day, what they're going to do is give us the language to let my input variables, x, y, z, whatever, let them kind of change simultaneously rather than one at a time, and think about, how do we quantify the rate of change of the output if all of my input variables are kind of changing at the same time. So that's the story of the next couple of days. We first look at derivatives from an isolated perspective of just a single one of my coordinates changing and all the other ones remaining constant. And then tomorrow, when we start talking about this in a vector context, we're going to let all of the input variables change at the same time and come up with a notion of derivative that uses vectors to shoulder the load of the difficult geometric questions that are involved. For us, there are sort of two goals, and so there's two learning standards associated with partial derivatives. The first one is computation. Just the pure ability to take a formula for a function of several variables and just compute formulas for its partial derivatives in each of its coordinate directions. So that's the first one. That's one of our core goals for the course. And the second goal is an interpretive goal. So to understand what the partial derivative of a function of several variables is actually telling us. What does it actually mean about the function? So those are separated into two goals, and so on your homework, they're going to be separated into two batches of problems. The interpretive goal is one of our supplementary goals. It's still important for us to understand, but you're only going to have to master it once on the homework as opposed to both on a homework and on a test at some point during the semester. Whereas the computational goal, you'll master twice before clearing it. So that's the roadmap, not just for today, but for our next class as well. Our textbook treats first partial derivatives and second partial derivatives as separate sections. So 10.2 is the section on first order partial derivatives. 10.3 is the section on second order partial derivatives. For our purposes, I'm treating first and second order partial derivatives as all part of the same set of goals for us. So there's not a separate goal for computing second partial derivatives compared to first partial derivatives, or interpreting second in terms of interpreting first. But in the textbook, they've separated it out into two sections just to kind of pace the conversation just a little bit. So let's dig in to what should a partial derivative tell us. We're going to kind of talk about the interpretive goals here first, and then sort of back our way into the computation of what a first partial derivative should tell us about a function.